Hello everyone, welcome to today's class. In this lecture we are going to discuss about one and onto functions. So let's go through the definition first. The definition, although yes, in the form of language it might feel slightly complicated, but if you understand it from diagram, I think that will be far too simple judging whether something is one or onto or not. Just give me 1 sec. I'll get the diagrams now. All right. Now let's understand from the definition itself. Okay, so now we have everything on the screen. Let's look for 1 So 1 says a function is said to be 1 if images of distinct elements under f are distinct. Now I will simplify this. I'll say every element should have one and only one image. Okay, every element should have only one image. Okay, and onto says every element y should have some element as x, means every y, every y should have x, some x, I'll say some x. Okay, every element means every x should have one and one image, means y. Okay, so every x should have only one y, then we'll call this as 1, otherwise it is called many one. Okay, and from a theoretical point of view, if we want to prove some function as 1, the implication is with this fx1. If we consider fx1 is equal to fx2, that means x1 should be equal to x2. Okay, we'll deal with this later. Right now you understand only this: every x should have one and only one y. Okay, all right, so let's check 1 for the function. The first one has one image. Okay, this is x, this is x1, x2 is written, although you can consider this as x and y also. Okay, every element has one image, every element has one image, every element has one image, every element has one image. So yes, 1. Okay, here every element should have one image. This element should also have one image, but the point is both images are same. Okay, so that's not 1. Every x should have one image, one and only one image. Problem is here two elements have one image. Okay, like this. You consider this as, why we call this as 1, because every one element of x should have one element of y. Here many elements of x has one y. As such, you can consider it like this. Okay, so there are two elements which have same y. That's not a 1 function, that's a many one. Okay. third, again same problem, two elements have same y, whereas our definition says every element should have one and only one y, which is unique as such. It should not be related with anything else. Okay. All right. So again, many one, and this is one has one image, 2 has also one image, which is again not related with anything, 3 has one image, 4 has also one image. So yes, pretty much all okay. This is also 1 1. Now let's check onto. Onto says every y should have x, whether it is same or different, we don't care. Okay, but every y, that's the keyword, every y should have some x. Okay, this is this definition, this is this definition. So now we have to see for ourselves in the reverse one. So this is y, it has x, yes, this is y, it has x, this y also has x, this y also has x, but e and f, these two values of y have no values of x, so this is not onto. Okay, whereas this has also has the same problem, b has some x, they are different but it has some x. Now we are not bothered with whether they are same or different or 2 values, 3 values, we are not bothered with it. But the problem is this a, this a does not have any x, so that's again not onto. Okay, whereas this one, a has some x, this one and this one. Okay, both 1 and 2 are the value of x for this a, but doesn't matter, as long as you have some x for it, that's okay. B also has some x, C also has some x, so yes, this is onto. Similarly here, A, B, C, D, everyone has some x. Okay, so they are also onto, so they are not onto, they are also not onto. Okay, so onto judging is very simple, every y should have some x, but 1 1, remember that one x should have one y, there cannot be two x with have one y or many y's. Okay, all right. I'll modify this one sec. You can understand this by this, like 1x should have one unique y. Unique y means it cannot be related with anything else. Okay. All right. So now if a function is is 1 1 as well as onto, it is known to be a bijection function. There are other names present for 1 1 and onto. 1 1 is also called injective. Onto is also called surjective. Okay, so when both the conditions are satisfied, 1 1 and onto, we call this as a bijection. Okay, I'll give you the definition also. Bijection or bijective functions. Okay. All right, so it is a function which is 1 1 and onto, or known as bijective. Okay, all right, let's now understand from the questions. Let's look at this question. This question will give you quite a good idea about 1 1 and on 2. Okay, let's see this. The question says a function is defined from n to n. This n to n means the first set, the value of x that you'll take is from the natural numbers, and the second set you'll take will also be from natural numbers. I think we have that. All right. So this is x, y. They are both belonging to natural number. Now they are being given from fx is equal to x square. Okay. So the numbers are natural numbers, so they will be starting from 1, 2, 3 and so on. Here also it will be 1, 2, 3, 4 and so on. Now what you do is just try to relate the elements. How will you do that? Fx is given by, y is your fx now. So fx is given by x square. So what is 1 square? 1. Okay. What is 2 square? That's 4. What's 3 square? That's 9. 4 square? That's 16. So this will keep going like this. So now you can see 1x has one unique y, 1x has one unique y, and it is not related with anything. So clearly this is 1, 1. And now try to think, what about this? Does every y has some x in it? 2. There is no element for 2. There is no x for 2. You'll say, no, it is possible that if fx is x square is 2, so you'll say x is root 2, but the problem is root 2 is not in the natural numbers. Okay, so that's why defining this, that they are defined in which sets, it's very important. Okay, so yes, definitely this is 1 1, but not on 2. Okay, so 1 1 is called injective and they are not on 2. Same question now. What they have done is they have taken the two sets to be instead of natural number, now they are taking z. Okay, so it will be having numbers from like minus infinity to minus 3, minus 2, minus 1, 0, 1, 2, 3, and here also it will be minus 3, minus 2, minus 1, 0, 1, 2, 3, something like that. Okay. Now you try to generate the relation. Second part says fx is again x square. This is x, this is y, which is fx, x square. So put the value of 0, 0 square is 0. Okay. Then 1 square is 1, minus 1 square is also 1, 2 square is 4, minus 2 square is also 4. So you can see 1x should have one unique y, but it doesn't have unique y. 2 also has 4, minus 2 also has 4. Okay, so definitely not 1 1. So I'll just put a tick and cross for like 1 1. No, on to every y should have some x. Point is, you can see we have some values already missing, 2 and 3, which does not have x. Also negative numbers, square of anything cannot be negative, so definitely negative number will not be related with any element x. So this is not also on 2. Okay, not 1 1, not on 2. So 1 1, not on 2. This is, sorry, not on 2. Second one, not 1 1, not on 2. Okay, third one is saying, I'll draw smaller ones now. This is the diagram for first, this is the diagram for second. Third, I'll draw here. the relation is again x square, but it is from R to R. So fine, R to R, x, y, fx. Again, all real numbers means all decimal, everything will be there. Na? 1, 2, 3, square root 2, square root 3, everything will be here. So right now I'm writing numbers like -3, -2, -1, 0, 1, 2 also. But there are number more than that as such. I cannot plot all the numbers. Here also same -3, -2, -1, 0, 1, 2, 3 and so on. Okay. Now since they are R to R, let's take the value of x and judge the value of y, and we have to see 0 again, 0 square is 0, 1 square is 1, minus 1 square is also 1. Okay, 2 square is 2, minus 2 square is also 2. Okay, so you can again see it's not 1 1, it's many 1. Okay. Many x have same y, so it's a many 1. Now what about, sorry, 2 square is 4, no? And by mistake, and I'll change this element 1, then 4, then let's say anything, 1, 4. So yes, it's a many 1, but what about the remaining element 2, 3? So yet 2 and 3 will also be related, but 2 here will be related with a number that's root 2. Okay, of course I have not written it on because I was taking only the whole numbers or the integers effectively. Okay, but 2 will be related with root 2. Similarly 3 will be related with, I'm writing here, as such I can write anywhere. Usually we have the tendency to write in order. So root 3 will also be related with 3. Now why root 2, root 3 is present now, why not earlier? Because it's a real number set, so all numbers are present basically. So every y, so far all the positive numbers are related, but still negative number is not related. So this is not many 1 and definitely not on 2. Sorry, this is not 1 1 or not on 2 also. So same problem with this also. 1 1 is not there, on 2 is not there. Okay. All right, let's check for now what is the next part. X cube, natural number, and z. So 4th and 5th, this was the third part. This was many 1 and not on 2. Third, 4th part, 5th part. So 4th part was from n to n, next was part from z to z, x, y, y is fx, which is x cube, y is fx, that's x cube. Numbers, natural numbers starting again from 1, 2, 3, 4. Here also it is 1, 2, 3, 4. Let's try to relate them. 1 cube is 1, 2 cube will be 8, 3 cube will be 27, 4 cube 64. So you can see again every single value of x has a unique value of y. Okay, so definitely 1 1. Okay, but every y, you can see these two y, 2, 3, they are not related because yes, 2 will be cube root of 2. Okay, but cube root of 2 cannot be written here. Why? Because this is a set of natural numbers. So this is 1 1, but not on 2. Okay. All right. Next is again same thing, if they are from integers, so -3, -2, -1, 0, 1, 2, 3, -3, -2, -1, 0, 1, 2, 3. Let's put, so 0 cube is 0, 1 cube is 1, 2 cube is again same thing, 8, 3 cube 27, -1 cube is -1, -2 cube is -8, -3 cube is -27. So pretty much again same thing, every single value of x has unique y in it. Okay, so yes, this is 1 1, but on 2 again you can see 2 3 still missing, because again cube root of 2, cube root of 3 are not integers. This is also not present, so 1 but not on 2. Okay. On 2 is injective, sorry, 1 1 is injective, on 2 is surjective. Okay, get comfortable with the other names also. Alright, so with the help of these diagrams, I think it is pretty easy to understand whether the given function is 1 1 or not, on 2 is or not. Okay, let's check for mod x. Mod is always a problem. Now mod x we already know, though they have given the definition. Mod x is if x is positive and it is 0, or negative if it is negative. Okay, so mod x is equal to x or minus x if x is greater than or equal to 0, if x is less than 0. Alright. In order to judge that, the domain is this is like the domain and range, or codomain and range basically. Okay. Let's take the value r na, so we can take any value r to r. So I'm still taking the easy numbers, minus 3, -2, -1, 1, 0, 1, 2, 3. Here also -3, -2, -1, 0, 1, 2, 3. Let's try to relate them. Mod of 0 will be 0, x, y is mod x. Mod of 1 is 1, mod of 2 is 2, mod of 3 is 3, mod of -1 is also 1, mod of -2 is also 2, mod of -3 is also 3. So you can see this is not 1 1, this is many 1. Many x has same y, so this is clearly many 1. And you can see there are all y should have some x, so you can see these y, negative value of y, they are missing x, because mod is never negative, so there will be negative values of y which are not related with any x. Okay. So this is many 1 and not on 2. Okay. Okay. Now let's deal with some MCQ form questions also. This is the basic idea for 1 1 on 2. R to R, again better draw it. Okay. It's very easy to understand if we draw that. Alright, for the x raised to power 4 question, x, y, y is fx, basically your x raised to power 4. This is r to r, so that means negative number, positive number, square root, cube root, everything will be here. So let's see. I'll start with negative. Minus 3, minus 2, minus 1, 0, 1, 2, 3, minus 3, minus 2, minus 1, 0, 1, 2, 3. If we take the value of x as 0, so 0 raised to power 4 is 0, 1 raised to power 4 is 1, 2 raised to power 4 is 16, 3 raised to power 4, 81, and so on. But if we do take the negative numbers, minus 1 power 4 is also 1, minus 2 power 4 is also 16. I think pretty much after this you can see what is going to happen. Is it 1, 1? No, it's a many 1. Is it onto? For onto, all values of x should, all values of y should have some x. So you might think 2 and 3 are not related, but see, 2 will be present here. I'll tell you which element will be there. If I take 4th root of 2, okay, now you'll say the 4th root will be a very complicated value. Yes, it will be, but point is, it is a real number. So if I take that, it will be related with that. Similarly, 4th root of 3 will also be related with that. So all positive numbers are dealt, but what about the negative number? Can any negative number be related anyhow? No. Why? Because power square is also a positive, so power 4, even powers are always positive numbers. So these values of y has no value of x, so it's not onto. So it's neither 1, 1 nor onto. Okay. For this question. So next one, he's saying fx is 3x, r to r. He's saying see if it is 1, 1 or onto. Now again, from this I think you can judge easily. So this time I'm going to try it to define this in form of a conventional manner. Okay. So remember other definition of your 1, 1. What was that? That fx1 is equal to fx2. If this happens, then x1 should be equal to x2. If we can generate this, no, if this is true and we can generate this, we can say that the function is, if this implies this thing, x1 equal to x2, then we can say function is 1 onto. This is applicable only for onto. So fx is 3x, so fx1 is what? 3x1 is equal to 3x2. I can cancel this 3. It automatically generates x1 equal to x2. So that means I can say this is 1, 1. Okay. You can draw this diagram and judge that also, but theoretically we can do like this also. Okay. Now it is 1, 1. Now we have to check for onto. So for onto the approach is slightly different. Okay, this is for 1, 1. For onto, what do? You generate the value of x. Okay. Y is equal to 3x now. So you generate the value of x. What is x? Y upon 3. And you put it in the, you calculate f of this y by 3. Okay. So that is 3 into y by 3. Okay. Because function, what is the function doing? Function is multiplying whatever you have written inside x, you're multiplying by that 3 with it. So if you have written y by 3, so it will multiply this. It generates what? Y. So if you can get your fx, which was f of y by 3 is equal to y, we can say the function is onto. I know it's slightly confusing, but that's the idea. You generate, first of all, for onto, you generate the value of x. Okay. Generate the value of x, put in the function. So I calculate f of y by 3. If it comes out to be y only, it's a onto function. So this is 1, 1 and onto, and you can judge it from your own diagram also. I'm not implying that you have to do it like this, it's just that this is another way to check whether a function is 1 1 and onto or not. Alright. Okay. Fine. I think that's it for this 1 1 and onto. Pretty much summarizes it. So just go through these diagrams again, it will help you to clarify all the things. This question was good enough to understand 1 1 and onto. Okay. And remember that in which set they are being defined, it depends a lot on that. Okay. All right, see you in the next class. Good day everyone.